All right, so this is rather odd. I'm in an empty room, but it's 2 minutes after 9, and as the saying goes, the show must go on. So if you want to see this material, you're watching the video, uh, but we're still going to go over, still have to progress in our notes. So the last thing that we were talking about is molecular species and how different molecular species are different from atomic species, and that molecular species have more energy levels. Not only do they have electronic states, but they also have these different energy levels in terms of vibrational and rotational levels as well. So that leads us to the clicker question, which nobody's here to do, so we'll be quick. So if we look at it, well, you are all, well, nobody's here to take it, so it doesn't matter. If we, the clicker question is, grab a clicker. You can be the only one to vote on it. So I'm collecting the video. So the question was, put the molecular transitions in order from the lowest energy to the highest energy. We talked about.
Oh, is this one?
All right, we got one vote, and that one vote says D. And if we look at what is the correct answer, I have it listed. But the largest energy is electronic. The second largest energy is vibrational, and the lowest energy level or highest wavelengths are rotational. So, good job. So,
That's referring to, like, we were talking about before, though, like the microwave.
yes.
Okay.
Yeah. So if we go back and think about the different transitions these occur in, so these are going to be occurring in the microwave region, right? So you're talking about centimeters wavelength. The vibrational transitions are occurring in the infrared, and finally the electronic are going to be in the UV vis. So each one of those is in a different region.
X-ray is considered electronic too, right?
Say again.
Is X-ray considered electronic too?
Yes and no. It's electronic in the sense that it's the promotion of electrons, but since it's core electrons, it frequently is associated with the breaking of bonds can occur. Usually when you think about electronic, you're just talking about valence. So X-rays are a little different. So now if we kind of think about where all these energy levels come from and the variety of different things that can occur, this is another energy level diagram that just shows the possible transitions and where we start to get complexity in our spectrum. So when we think about infrared transitions or microwaves, so infrared transitions are going to be within a given electronic energy level, where the darker lines here, E0, E1, E2, represent electronic energy levels. And then we've got vibrational levels within each one of those electronic levels. And in truth, it just gets too messy to show, you also have another series of levels that are rotational energy levels within each one of the vibrational states. Okay, so there's really a host of different places where you can have transitions. So these smaller transitions that could occur that were sub-energy level, those would be rotational transitions that can occur. Now, where it becomes significant for us is that realizing that when you have an absorption of a molecular species in the visible or the UV region, if it goes from one of these lower states, it not only can go up to this electronic state, E1 or E2, but it also could land on one of these vibrational excited states. So the E primes represent vibrational energy levels. And we have to realize within each vibrational energy level, there are multiple rotational energy levels that can exist. So it really becomes, we talk about the energy levels being discrete, and there being discrete transitions that occur with each one of these transitions, but because of the embedded vibrational and rotational energy levels, it becomes a continuum for molecular species. That's the reason they're big, broad peaks. So that's what happens when energy is absorbed. It's still quantized in the fact that the energy of the photon, h nu, so Planck's constant times the frequency, is equal to the difference in energy from whatever the ground state was, or whatever is being populated. And again, at the ground state, it may be at this vibrational zero level, but unless you're at absolute zero, you're never going to be there. So more likely, you're starting off from one of these is where your initial event's going to occur from. So that's somewhere it's an electronic ground state, but vibrationally and rotationally, it's not going to be a ground state. You get excited up to a higher energy level, and it can absorb at one of those many different points. All right, so when you absorb a photon, that's not an energetically favorable place to be for a molecule, so it's going to try to lose the energy off. And there are two different processes that can lose energy off. One's called non-irradiative relaxation. And the simple way to think of this is it's a series of vibrational energy losses where it shakes the excited energy out. Okay, so you have a vibrational energy loss, a series of steps, and then you have this jump. We're going to talk about this jump in a little bit as we go further into the chapters. But in this one, you have a jump between electronic levels, but it's non-radiative. Maybe it's a bump or collision with another molecule or the container solvent molecule. But there's a series of steps that are small energy losses that are non-radiative. Frequently what's going to happen is that you get to a point where you lose off some vibrational energy. So these would represent vibrational and rotational energy loss. And then you do a step over once you're at that vibrational ground state in an excited electronic state. That's frequently when you lose off a photon of light. All right, so in this case, we excite maybe to this, change my colors. We maybe excite to this state, and then through a series of vibrational losses, we lose energy down to this level. Now we're in this electronic excited state, and this electronic excited state could emit a photon off, and it could emit off in a molecular species in a variety of different levels, because as it falls back down, you not only have this electronic ground state, but you still have those vibrational levels. So when you have emission spectra for molecular species, they're going to be broad, just like absorption spectra. Okay, they're not going to be sharp and discrete. So it just kind of gives us an understanding of how molecular spectra different from what happens with atomic species. So the take home out of that is molecular are characterized by continuous spectra. And if you look at the old tests every other year, I'm going to ask you to explain that. So that's something we just have to understand. All right. In the UV vis, it's electronic transitions. In the infrared, it's mainly vibrational. There's just a few rotational transitions that are coupled with that. Now, if we will expose our sample to a magnetic field, we can actually get some new energy levels there. Okay, so if we look at energy levels that exist at the lower energy within a molecule, there are some separations that occur only in the presence of a magnetic field. And those deal with the spin of the nucleus and the spin of an electron. So what I mean by these, if you look at the spin of an electron, those energy levels are the same without the presence of a magnetic field. But if we'll apply the sample into a magnetic field, it causes a separation of those two energy levels, those two spin levels. So you have a If you want to think of it, an E of an upspin and an E of a downspin, that are now separated in two different energies. And the greater the field strength, the greater the separation. That's the reason in NMR, the bigger the magnet we use to put the sample in, the higher the resolution, the more those energy levels are separated from one another. So that works the same in the spin of the nucleus as well as the spin of an electron. The spin of a nucleus is electron spin resonance spectroscopy. The spin of spin of an electron is electron spin spectroscopy. So ESR, electronic spin resonance spectroscopy is what it's called. And then the spin of the nucleus is the one we're more common with if you've had organic NMR, nuclear magnetic resonance spectroscopy. But both of these typically are going to occur, it depends a little bit on the magnetic field strength, but they're going to occur in the radio wave regions. In ESR, you're talking about 9,500 megahertz. In nuclear magnetic resonance, where you'll use much higher field strengths, up to 900 megahertz. There's actually been I think there's 1,000 megahertz magnet that's been produced, but there's only a few of them been made. It's very hard to get a stable field strength when you get a magnet that big. So you're talking about a magnet that's a million times the magnetic strength of the Earth's natural magnetic field. And you also have to contain that magnet. That's a big thing, is that you want magnets in these devices that are shielded in the way that things like pacemakers are affected by magnetic field. So even the old NMR that we had, nobody could come within 10 foot of it with a pacemaker on. And it would potentially disrupt the signal for a pacemaker. And that was with a magnet that was 4.7 Tesla, or 47,000 Gauss field strength. Okay, so the more powerful the magnet, the bigger the separation energy, hence the bigger magnet. Now, once something's been excited, it goes back down to the ground state fairly frequently most of the time, and sometimes it goes by the non-radiative radiative path like we looked at. Sometimes it emits light off. If it emits light off, that becomes another form of way that we can study the sample. So we can look at sometimes the absorbance, the capture or the excitation event, excitation and absorbance meaning the same thing, or we can look at the emission event that occurs. So as we think about these, the difference in spectra that we see, just to reiterate this, atomic species, very sharp lines. Molecular species typically are characterized by these broad continuums. Sometimes the continuums, in the example of benzene, the thing that makes benzene have so much shape associated with it is that you have a structure that is very repetitive. Every carbon, every hydrogen is equivalent on benzene. So electronically, even though it is a molecular species, it almost is mimicking to some degree an atomic. It's a very simple, like a couple atom system. Okay, we're going to look at the emission events first and start talking about those. So in the emission of radiation, the relaxation event is when you go to a lower energy level, and sometimes that occurs by the release of photons. How often is it with radiative versus non-radiative? It really depends on the sample. Some things will are more prone to emit light off depending on the structure. If you look at, there are some compounds, when we talk about the fluorescence chapter, there's a compound called fluorine, and it has almost 100% probability that when it captures light and is excited, it's going to emit a photon back off. And other things may have efficiency of emitting light back off of 1 or 2%. And it's everywhere in between. So it really is structurally dependent, and it not only becomes structure, it also depends on the environment as well. If there are things that are heavy solvents around, there are a lot of things that can influence the emission. But when we talk about emission, we can talk about both molecular and atomic species. So we can get emission that results from a couple of different ways. In particular in this, we're talking about what would happen with with atomic species, individual atoms. You can bombard it with electrons. You can expose it to a high potential spark. You can expose it to high temperatures. So enough thermal energy will cause an electron to be excited to a higher energy level, and it could fall back down. And you could also hit it with a beam of electromagnetic radiation. It could capture that, and then it could emit back off. And when we have emissions, if it's atomic species, they're going to be sharp emissions, lines. If it's molecular species, they're going to be continuums associated with it. One of the types of ways that we look at how things emit energy off is with thermal radiation. If you take any substance and if you heat it enough, it's going to start glowing. And typically we're used to seeing something like a stovetop burner, electric stovetop, will glow red. Well, that's emission of thermal radiation. So there's enough heat produced by ohmic heating, electric current is flowing through that heater element, that it causes that metal to reach a high enough temperature that the electrons are being excited to a higher state and they're emitting back off, emitting light off. Now, different substances emit at slightly different regions, but for the most part, the emissions follow that of what we call a black body radiator. So if you take a black box and you heat up that black box and you put a hole in it and look where light can come out of it, if you just keep applying enough heat, eventually it's going to start glowing, emitting light off. And if you look at how those things shift, here's an example of black body radiator at 2,000 degrees. The light now is well up into the near IR. So if we think about the visible region, it's down here in our 500. So we can't even see that light. But as it gets hotter and hotter at 3,000 degrees, now it's starting to give off a lot of visible light. And you could actually feel the heat coming off of it. There are several, I bought a little heater and put it in my shop to help keep my dogs warm in the winter. And it's got it's an hour emitter. So it works on a process. It's got 2 strips and black body radiator, and it's got a big mirror in the back of it. But it just passes current across this, gets it hot, and it emits off. Even though it emits off some visible energy, the main heat that it's coming is emitting off is this stuff that's heating things up in the IR range. And if you get hotter and hotter, it starts to shift towards lower and lower wavelength. So by the time that you get things that are different type of lamps we can use to get different types of information, because they become now matching the wavelength regions we want. A common one that we use is a xenon arc lamp. It emits strongly through all of the UV and the vis. All right, so if we think of the UV starts down here about 200 and goes up to about 700, it's got a very strong output there. All right, a tungsten lamp, a tungsten halogen lamp, traditional filament light bulb. They work pretty good in the visible, but actually most of their energy is expended in the IR. So one of the downsides to a tungsten lamp, if you shine from a regular light bulb, if you just shine the filament light bulb on your sample, it's shooting a lot of infrared in there. Eventually it's going to heat your sample up. So if you have something that's temperature dependent equilibria, okay, anything, and most chemical systems are temperature dependent, you're going to have a shift over time. So you want to minimize your exposure to the sample. So we can have thermal radiation. We can have the emission of X-rays. So we talked about X-rays a little earlier. So when we strike a sample with a high enough energy photon, it causes a core electron transition. So an electron in the core gets kicked out or promoted to a higher state. It could be either one. And what happens is the excited atom returns to the ground state by a series of electron transitions that result in a cascade event. So if we think of going back to a very simplistic energy level diagram, so you've got, let's say, you've got 1s electrons and 2s electrons and 2p's and 3s's and 3p's. Okay, so you got electrons in here everywhere. So these lower energy levels are filled, and let's say you've got a valence electron So this would be your outer shell. These are your valence electrons in the threes. You hit it with a high enough energy photon that it causes this 1s electron to be ejected. Okay, so this electron gets kicked out. So that leaves an empty hole down here, and the fact that that electron is no longer there is going to cause this cascade event. So this electron may drop down and fill its spot, then this leaves a hole. But when this one falls down, it emits light off, so there's a photon emitted here. And then maybe this one falls down in that one's place and emits photon off at different energy. But it's very characteristic because these energy levels are known. It's a very characteristic pattern that we can look at. Now, the good thing about this is that typically this technique, which is called X-ray fluorescence, is non-destructive. So you can take something that's very valuable and you can find out what its atomic composition is. Normally, when we find out what atomic composition is, we take a sample and we digest that sample, break it down to atomic form, and we put it into an extreme heat treatment. And we look at the emission spectra that comes off of it. But you couldn't take a valuable piece of art and do that too. Okay, but this technique lets us hold the X-ray spectrometer, fluorometer, up to the piece of art, just shoot it with a little beam of X-rays and look at how it glows, what it emits back off. So this is good when you have very valuable artifacts. If you go to the Smithsonian in DC, if you ever get to go to the archives down the bottom where they're researching new materials, they don't always open that up, but there's several of those instruments in use there. And one of the things that they'll do is they'll characterize a painting, they'll look at it and they'll scan the whole painting in with X-ray fluorescence, and they'll know absolutely every element that's there to characterize the pigments that that artist uses. And they have a pattern that they know what Rembrandt uses for greens and for blues and reds, and that becomes predictive. If there's a potential forgery and if it doesn't match what the known patterns, that's going to suggest that it is a forgery.
So exactly what type of information is, like, when you're doing that, what is it telling you? Like, is it telling you, like, how many energy levels it has? Or, like...
Well, the spectra that's going to emit back off, if we look at it, it's going to look just like a spectra that we're used to seeing. So if you look at wavelength versus signal, you're going to get, depending on what the energies are with these different transitions. So if this is a big jump, this would be a higher energy or a lower wavelength.
So it's showing you the transition.
It's telling you the transitions associated with that particular element. Because the same way that if you look at the excitation events, even though we talked about how if you looked at potassium and magnesium, they both have the same valence electrons. So this has a 3s1, this has a 3s, it's got two valence electrons in it. They have completely different spectra because the nuclear charge is different. The same thing associated with this.
Okay, so like each element.
Each element's got a unique pattern associated with it.
You can just quantify it just by the filters.
Exactly. Yeah. Now it's a little harder to quantify with this technique, but it certainly can be done with a good degree of accuracy. So there are two particular techniques that we look at that are first cousins: fluorescence and phosphorescence, that are the study of light that's emitted by the absorption of radiation. So you strike it with UV vis light and you look at the light that's emitted back off. Or in the case of X-ray fluorescence, you're actually striking it with an X-ray and looking at the light that gives off. The difference between fluorescence and phosphorescence, and we'll talk about those as we cover those chapters, it's just time. Fluorescence is a rapid event. It occurs in less than 10 microseconds. Phosphorescence is a very slow event. It'll occur in something greater than 10 microseconds up to minutes or hours. Anytime that you've seen something that glows in the dark, commonly that is a phosphorescence. So something where you hold it up to the light, turn the lights out, and it glows bright, and then it starts getting dimmer and dimmer and dimmer in time, that's a phosphorescence event that occurs. And that phosphorescence is very rare in nature. There's not very many things that phosphoresce. About 3% of all known atoms and molecules in nature fluoresce. Phosphorescence is much less than 1/10%.
Like phosphorescence. something glow like that.
Well, the ones that glow, they're not taking light in. They're glowing on their own. It's chemiluminescence, like the algae does. We see phosphorescence more commonly in rocks and minerals. Okay, so resonance fluorescence is when the energy emitted off is exactly equal to the energy absorbed. And I tell you that this occurs primarily in atomic species. So my question is, why do you think it would occur in atomic species? Why do you think, and I'll give you, I'll go back a couple slides as a food for thought thing. So when we're looking at this, this is an example of a molecular. All right, so in the molecular, we absorb up here, and then we had some vibrational energy loss, and then we had this drop. So why would it be different in individual atoms?
And I guess because they would absorb the energy.
There's no vibration on the rotational levels. So now if we go back and think about, I'm going to jump backwards again. If we think about what's happening in atoms, in individual atoms, the only thing you have are these dark lines. You don't have all those sublevels. So now you can just go from to those dark lines, and that's the only thing you can have. And that's what makes atomic spectra much cleaner and sharper lines, more defined in their nature. Now here's an example of a emission spectra. That this is done with flame spectroscopy. You just took a hydrogen-oxygen flame, which is burning about 2,600 degrees, and basically this is a Bunsen burner with those, and you're aspirating in, this is brine salt water. And it's glowing with the colors that of the alkali and the alkali earth metals. Most of them can be thermally excited at 2,600 degrees, and they emit off very characteristic lines. So sodium has an emission signal about 330. There's actually two of them close to there. Potassium has a signal at 404. Calcium has a signal at 423. And if we isolate those three signals, those are the three that we typically look at to quantify those electrolytes. In fact, if you go to the doctor and you pee in the cup and they want to check your electrolytes, common thing when somebody comes in, they suspect they're dehydrated, or elderly people that maybe have become dehydrated, a variety of different things. They'll take the urine, they'll typically dilute it 1 to 100, and they have an instrument that has 3 different filters in it. And those filters will isolate. It's got a detector sitting behind each filter. One isolates this region for sodium, one does this region for potassium, and one does this region for calcium. And very quickly, they can get a measurement, just shooting it into a flame, and they've instantly got a measurement of what those electrolytes are. Okay. Now, the molecular species, there are some molecular species that the hydrogen-oxygen flame allows. It's not hot enough to destroy. And you look at them, the MgO bands, but now you start to see the characteristics of a molecule, broad things that are associated with it. Now, there's also a few other things in here that when you look at some of the other detail, there's a strontium signal. So this is salt water. Everything's going to be in salt water. The good thing about something like sodium has a number of transitions, and every element does. Now, some of them we're not seeing because they're further down the UV, but here's the calcium hydroxide. The big honking signal, if I looked at what this looked like, this is actually on top of the building where this is leveling off, because the bulk of the light is this sodium that's coming out. The bright orange glow that you would see with this is the overwhelming signal that you have from the sodium. It's by far the biggest transition that's in there. But by looking at a couple of things, we can get some assurance of this data. What I mean is that if I'm quantifying this signal, I know that the ratio of whatever these two sodium signals should be, if it's a a 2-to-1 ratio in the heights of those, that I could do a backup check. If I quantify with this one, and I might want to make sure that it's not being interfered with, it's a good signal, I could compare this signal at a little bit less than 500 and say, is it half the height? Okay, so it's a predictive spectrum. So there's a lot of information you can get with this, and I'd say that, or tell you that you can overcome where you've got all this molecular stuff, you can overcome that with heat treatment. Okay, if instead of burning at 2200 to 2600, which is about what you can get out of a hydrogen oxygen flame, if you take the heat up to 3000 plus, almost everything molecular in there would disappear. Now, there are certain things that are stable up to 5,000 degrees. It just depends on those particular materials. All right, so we said resonance fluorescence, which is what happens with these particular species. This is emission, but they would absorb at the exact same wavelength. So if I wanted to know where would sodium vapor absorb, well, it's exactly the same wavelengths that it emits at, because atoms undergo resonance. So sodium's 330, potassium's 404, calcium's 423. They don't have anything but vibrational energy levels. Now, the non-resonance emission events we have, that's when the energy of emission is not equal to the energy absorbed. Vibrations occur very quickly, so vibrational transitions occur in the oscillation of a wave of light, so they can, much like in a photon capture, so a femtosecond. So what happens is you can lose a lot of vibrational energy off before an emission event can occur. So what happens in atomic species, this energy level diagram represents what we have in atomics. There's nothing but these electronics levels. So again, the dark lines represent E electronics. So you can have a absorption or an excitation event, and then you're going to have an emission event. So this is a 330 line of sodium that's exactly the same energy. Okay, so that's resonance fluorescence. Now, what happens with molecular species is that when you have your excitation or absorption event, is that it goes up, and this is just to simplify the graph, they show it going up to an electronic ground state. But I just want to emphasize, in reality, there's all these other vibrational levels in here that are coexisting. So it could go up to any of these other ones too. All right, so it's not just limited to that one. But when it falls back down, you've got the same thing. It can fall back down to the electronic ground state and vibrational ground state, but it could be in any one of these other excited states as well. So with molecular species, when even you're doing emission, you get broad spectrum. Okay, so continuums. Continuous spectrum. Broad peaks. All right. So when we start trying to quantify the things that we can see when we're quantifying, is we can look at the power associated with a signal, and we look at the different classes to look at it a little bit differently depending on how we're doing our type of spectroscopy. If we're doing an emission event, what we're simply doing is studying what is the power of that emitted signal. The power of that signal is directly proportional to the concentration. That's with atomic emission. If we're doing a luminescence event, meaning we're striking it with light, we're looking at the light emitted off, we're looking at the power of the emitted signal. But still, that power is directly proportional to concentration. So if I've got a detector that can see power, it will be proportional to the concentration. That's one of the reasons I wanted y'all to see how could we modify that signal to make it a linear response. From our lab data that we had with our electronics lab. The one we won't talk about very much, but has some purpose, is scattering. You can look at power of scattered light, and it's proportional, so that's used in things like Raman, particle size analysis. Those are a little bit more specialty, but the big one we'll use is absorption, And with absorption, we look at the power of the incident light. So how much light goes through a sample that represents a blank versus how much light goes through a sample. And we call the blank P naught, and we call the sample, the light that goes through the sample P. The negative log of the ratio of P divided by P naught is equal to absorbance. We'll define that on the next page, and that's what's proportional to concentration. And it doesn't matter if we do atomic or molecular absorption, it works the same. Now, we've done this with 2 techniques in the lab so far with the Shimadzu. We're going to do it with another technique, doing molecular spectroscopy next week. So on all of these measurements, so any of the 4 above, it requires that we have a detector that can monitor the power of the radiation, either transmitted or emitted signal. Our detector is going to see a signal, which is going to be typically monitored as a voltage. There's a few things where we look at current. Diodes measure current flow, but most of the other ones we're looking at voltage that it kicks out. So there's some type of, even the ones that like a photodiode, it was a current flow that's changing. We looked at the current flow across the resistor to measure the voltage drop across that. So we can convert that current into a voltage fairly easily. So you have a signal that's directly proportional to the radiant power that we have in a signal. But what we find is that almost all detectors have a signal that exists in the absence of light. So if I take my detector and completely put it in the dark, it's still emitting a little bit of a signal, and we call that signal the dark current. So that's basically, if we plot the signal versus the power, that would be where the intercept is, if you want to think of, I like to see things graphically. So if you looked at power of the light versus the signal, so this being the 0, and we'll just use arbitrary 100 going up, that the fact that with the 0 power, you still get some signal. That intercept represents the dark current. Now we can adjust that typically with our instruments. This is where we adjust or offset that. So correct or offset. Set with 100% T sample or a blank. So what we're typically doing when we run a blank is we're adjusting that so it just goes through the origin. Okay, so that's the purpose of running a blank sample. All right, so emission versus absorption. Emissions are the simplest in terms of equation-wise. Signal is directly proportional to concentration, which we measure that signals are power, so we simply do a plot of the signal versus concentration, and it's going to be a straight line. It's linear. In absorption techniques, that's what we're looking at in these other 2 guys. Now what we do is we're going to transmit a beam of light through our sample, and we have to know how much light's actually making it through the sample itself, and versus how much is being captured. Now we know that due to reflection, that some of the light, every time it hits one of these interfaces, it's going to be reflected back. So every time it runs into an interface with a different refractive index, that some of the light's going to be reflected back. So not all of P that's coming in here, or P naught's going to be transmitted through. So what we do is we run a blank, and we make our measurement based on the blank. So P naught actually becomes the P of the blank. All right? So that's what we're actually doing. So transmittance is defined as the ratio of the power transmitted from a sample. All right? So this P represents the sample, and the one on the bottom, P naught, represents the blank.
So that should always be less than 1, right?
The transmittance should be less than 1, and frequently we'll express this as percent T. So multiply it by 100. So if it's percent T, it could have a possible range from 0 to 100. Okay? The absorbance is defined as the log of the ratio of P naught over P. So here's the same equations a little bit bigger. So transmittance is the ratio of P divided by P naught. Percent T is simply that ratio multiplied by 100. Absorbance is the negative log base 10 of the transmittance. And if we want to take and apply our negative through, instead of doing P over P naught, if we apply our negative through, that's the inverse function of a log. So log of 1 over A is equal to a negative log of A. Okay, so we can use that inverse function of a log, and we can take and flip these around. So it's equal to the log of P naught divided by P. And the reason we want to do that transition is because this is what gives us our linearity in our sample. Now absorbance is directly proportional to concentration, and there are two parameters where there's only one parameter with an emission signal. Now it depends on how much sample we shine the light through. How wide is this thing? So what is the path length? That becomes one of the terms that's going to determine our absorbance.
There's a standard unit used for path length, like centimeters.
Typically centimeters.
Okay.
Yep. And I say typically, when we do stuff with cells, 1 centimeter path length is a standard. But when you start doing other types of measurements, it may be the diameter of your of a tube. Like when I do my technique with capillary electrophoresis, I'm using this tiny tube that's made out of quartz, fused silica, and it has an internal diameter of 50 microns. All right, so that's a fraction of a centimeter, right? And I'll actually shine the light directly across this, and we'll look at, based on the molecules that are coming through here, how much light's transmitted through. So on this one, I don't have as strong of an absorbance because my path length is tiny. But there you need a more sensitive detector.
And the concentrations you're doing with that are really small though, right?
Typically, yes. So usually the upper limit on concentration is something like 1 millimolar. And usually your concentration you're working with are the micromolar range. And if you're doing something like a laser-induced fluorescence, could be orders of magnitude lower than that. All right. So here's a couple of clicker questions that are a couple of questions from old exams. I would work these just to show you some of them. So this number 6 says you had a sample in a blank, had percent T of 45.4 and 97.5. So this one's the sample. We're still writing here. So this is the sample, and this one's the blank. All right, so what is the, how would we calculate the absorbance? Well, absorbance, we know that this transmittance is directly proportional to the power. So if you want to think about it, it's the ratio of percent T's. All right, so, but here I gave you your power. So if you want to think about this, percent T would be P of the sample divided by P naught of the blank. So let's see, let's get her. It would be 45%, all right, transmittance divided by P naught, and then 97.5% divided by P naught. The P naughts would cancel out if you think about the ratio of that. So that would be my transmittance ratio of the two. So if I look at how do I calculate the absorbance to it, the absorbance is going to be the ratio of the log of our P naught. So 97.5 divided by 45.4. That comes up to be one of my numbers. It's log base 10, and yeah, I get the first answer. All right, so that's how you would do that one. The second one says a chemical system obeys Beer's law. The sample concentration is 1.25 times 10 to the minus fourth, and that gives a 10% transmittance in a 1 centimeter cell. What's the concentration going to be if it yields a 20% transmittance? So now if we look at applying Beer's law to this, we want to take this relationship, absorbance is equal to absorptivity times path length times concentration, and we want to take the known system. So our known system here, we know the concentration term, and we know the percent T, but I can convert percent T into absorbance. So I'm going to take the known, and I'm going to find out what is this term, because it still ends up, the equation is absorbance is equal to a constant times concentration. And that constant is the combination of A times B, or molar absorptivity times path length. So what I'm going to do is take and find out what the absorbance is for the 10%. So absorbance is equal to 2 minus the log percent T. So if I throw that in my calculator, 2 minus 10% log, it's going to be exactly 1 is going to be my absorbance. And now I'm going to take and solve for what is K. K is going to be equal to the absorbance divided by the concentration. So 1.25 times 10 to the minus 4th. So it's just going to be the inverse of that. And I get 8,000 is my value for K.
What exactly is K?
K is just the product. These two things represent a constant. So it's the product of absorptivity times path length. Okay? So from that, I can find out, apply that to the unknown. So I know my unknown, if I look at the absorbance of the 20%, so 20% T means the absorbance is equal to 2 minus the log of 20%. So we'll find out what that is. So 2 minus 20% log. So that's equal to 0.699. So now 0.699 is equal to the K, which we just found was 8,000, times the concentration 2, or the unknown here. So when I just take that and divide it, I get the concentration is 8.7 times 10 to the minus 5th. Hopefully I got an answer that matches that. 8.7 times 10 to the minus 5th. Put a number in wrong then. Minus okay, I'm gonna check everything. Minus 10% log. Okay, that's 1. 1.25. That's 1.25 e to the 4th minus equals. That's 8,000. That's right.
And,
2 minus. Yeah, go ahead.
it's the absorbance equals 2 minus log of percent T. Is that like one of the equations?
Yes, that's is this equation. Okay. If you put it in forms of transmittance, it's the same thing. So the multiplying it by the 100 is where the 2 comes in when you take the log. It's the same equation though.
No, because you don't have the like the blank, so that's you'd have to use it that way, right?
Well, if you want to think about it, putting it in this form of the equation instead of percent T, you just put it in as 0.1, and it would still give you the same value out of it.
So if you just do 0.1 log, then you'll get the same value.
Yep. All right, so divided by 8,000. Tricky me. Let's see what I missed. It's a wider cell. So that means you'd really need to solve this in terms of molar absorptivity. So this was times a 1 centimeter cell. This one has a 2 centimeter cell. So we take the number divided by 2. Yeah, there's where your answer C is going to come in. I didn't read the entire question. I stopped right here and didn't read that it's 2 centimeter cell. Okay. Well, that's for the most part the end of this chapter. I really encourage you to look at problems like this. The ones at the end of the chapter. Look at the ones from your old analytical book. There's some analytical books in the seminar room. Make sure you can do these Beer's Law things. It's the things we've been doing in the lab, but make sure you can do the conversions from percent T to absorbance. Okay? Be proficient with those. Because we're going to apply those same type of calculations to every different type of technique that we do.